Right, so in this discussion in our chemistry, I want to talk about bond energy or bond enthalpy as we may call it. But what exactly is a bond energy? So when we talk about bond energy, you can simply say that it is simply the amount of energy absorbed or released in breaking or forming one more of a covalent bond. So we can write that and simply say is the energy absorbed or released in breaking or forming one more of a covalent bond. So this is what we call as being bond energy, sometimes as we call it as being bond enthalpy. So we are simply saying the energy absorbed or released in breaking or forming, in this case, or forming one more. The key word is that, you are looking at the energy that is absorbed in forming one more of a covalent bond or breaking one more of the same covalent bond. For example, if you look at hydrogen chloride here, this is a bond that has been formed. Now, how much energy do you need to break it in this case? Let's say if maybe the energy that is required to break this bond is 256 maybe kilojoules per mole of energy, meaning that if you were to form the same bond, hydrogen reacting with chlorine, you would actually require, the same amount of energy, which is in this case 256. So just one more of that covalent bond. So that is what we call as being bond, energy. So just a few concepts that you need to remember. Remember, it is the same energy given out when making the same bond. That is what I simply said here. Now, when it comes to, to bond, energy, this bond energy actually measures, the strength. So it will tell you the strength about a covalent, bond. So it measures the strength of a covalent bond. So that is what you need to remember. So it actually, measures the strength of a covalent bond. Now, the way it follows is that, the stronger, the bond. So the stronger the bond, the more energy. So the stronger the bond, the more energy, required to be taken in order, to actually, break this bond. The more energy. So in order for you to form the energy, the stronger the bond, it simply means that more energy has, to actually be taken in so that you're able to create this bond. And the other idea, or the vice versa, is also the same. You need to remember that the stronger, the bond, formed. So the stronger the bond formed, the more energy that is actually released. Okay, so that's the whole idea. So if you're looking at a stronger bond that has actually been formed, it simply means that the more energy that is going to be released. Now, just a few tips that you need to remember about this one. A few tips that I want to actually give you concerning bond energies that you need to remember is that, one, you need to remember that bond breaking, or when you're breaking a bond, it is simply an endothermic reaction. So bond breaking is an endothermic, so it is actually an endothermic reaction. Why do I say that when you're breaking a bond, it is actually an endothermic reaction? Well, it's normal. When you want to break a bond, it simply means that heat energy has to be taken in so that you can break the chemical bond that is actually holding the two atoms. So bond breaking is simply an endothermic reaction. On the other hand, you know, bond formation, or let me just say bond formation or bond forming. So bond formation. So bond formation is an exothermic reaction. So whenever you are forming a bond, it simply means that you know, energy has actually, you know, to be given out. So when a bond wants to form, it simply means that energy is actually going to be released here when a chemical bond is actually being formed. So that is what you need to remember in that context. Now we need to again understand that it is possible that we can actually calculate what we are calling as being the enthalpy change. In other words, the energy change in a chemical reaction using bond energies. So in order for you to calculate you know, what we're calling as being the enthalpy, so in order for you to calculate the enthalpy change using bond energies, so the energies in the bonds, the formula that we are going to be applying, or that you need to remember, is that the enthalpy change represented by delta H, the enthalpy change represented by delta H is equal to the summation of the bonds that are broken. So the summation of all the bonds that are broken minus the summation of all the bonds, you know, that are formed. Now remember, if you have a reaction in this case, where does bond breaking take place? For example, if you have in this case, maybe you have let me say you have A plus B, you know, to form up AB. In this case, you are going to find that usually, you know, bond breaking is actually going to take place, you know, is actually going to take place. Let me maybe illustrate it nicely like this. You have got AB plus CD, but you form up in this case, you know, A, you know, D, and you form up, you know, maybe C, B there. It simply means that on the reactant side, you realize that bonds are actually, you know, broken. So on the reactant side, you find that bonds are going to be broken. Then on the product side, you realize in this case that you know, bonds you know, are actually being formed. So therefore we can also say you know, we can also write this formula and simply say, if you want, the enthalpy change is equal to, in other words, it is the energy of the reactants minus, in this case, the energy, in this case, of the product. Why? The energy of the reactants and energy of the product, because on the reactant side, bonds are actually being broken, and on the product side, you know, bonds are actually, you know, being formed. And this is the formula that we are going to use in order to calculate the enthalpy, you know, change. So I want you to realize in this case that your ER is representing the total energy, you know, the total energy to break the bond. So the total energy required to break the bonds, and EP there is representing the total energy released, if you want, in forming new bonds. So the total energy needed in forming new bonds. So total energy you know, required, if you the total energy, if you want, you can simply say required to break you know, to break, you know, odd, if you want to break odd bonds. Yeah, to break odd bonds. So that is what we mean there. So that is what that is representing. And of course, remember, our delta H is representing the enthalpy change, and that is what you need to remember. Now, of course, a key concept that you need to remember, again, let me give you a few notes that will prove to be helpful for you. If the energy of the reactant is greater than the energy of the product, then you should be able to know that it is an endothermic, it is actually an endothermic reaction. So you need to remember it is an endothermic. So when the energy, the total energy of the reactant is greater than the energy of the product, just know that it is actually an endothermic reaction. 2, if the energy of the reactant is less than the energy of the product, then just know that it is an exothermic reaction. So in most cases, they are going to be giving you what we call bond energies. So they'll give you bond energies of what is actually reacting, then you should be able to calculate. Let me just look at just one example in this discussion, but in my next video I'm actually going to look at more examples. Now I want you to understand, for example, for any covalent bond, let's say that they have actually given us a covalent bond. So they'll give you a table likely, and they'll give you what we call the bond energy. So they'll give you the bond energy, and of course the bond energy is given in kilojoules per mole. So the bond energy is given in kilojoules per mole. Let me say for hydrogen, because I want to use it, the bond energy in this case is about 436. And let me give you for another one, fluorine, the bond fluorine, in this case it is about 158 kilojoules per mole. And of course, let me give you for hydrogen fluoride, in this case that is about 568. So you don't need to worry about these bond energies. In most cases they are going to give you in the exam, so you don't need to actually worry about that. They'll give you all that. So let me say maybe in my example and simply say calculate the enthalpy. Let's say calculate the enthalpy change in the formation of hydrogen fluoride from its elements. Of course, when I talk about the formation of hydrogen fluoride, of course it will mean when hydrogen gas is reacting with fluorine, which is actually diatomic. And of course, when hydrogen reacts with fluorine, you are going to produce hydrogen fluoride, but which is actually also in gaseous form. You need to balance up the equation, so I can put up a 2 there. So now, how do we calculate the enthalpy change or the heat of the reaction in this case? Well, it is very simple in order for us to calculate that. Remember, now when I talk about hydrogen, hydrogen is reacting with fluorine in order to produce hydrogen fluoride. So let's look at you need to write the bond line formula for hydrogen fluoride. So it is simply hydrogen and hydrogen. There you actually have fluorine and fluorine, because there are 2 fluorine and there's always a single bond. And remember, when you talk about bond energies, it has to deal with what we are calling as being covalent compounds. Not ionic, but of course covalent compound. Here you have got hydrogen fluoride, but if you look at hydrogen fluoride, how many hydrogen fluoride are there? According to this, it tells you there are 2 molecules, so you can put up a 2 right in front of that. So you have seen the way I've actually done them. I've written bond line formulas to show all the bonds, because we want to account for all the energy in this bond. So what's the energy between hydrogen and hydrogen? Well, it is simply a 436. Fluorine and fluorine there, it is simply a 158. That's what we know. And there, for hydrogen and fluorine, from this table I've given you, so it will be 2. It is 568, but because there are 2 of these bonds, so multiply by 568. So that's what we are going to do. So we can actually get to use a calculator. Now if you add all this, in this case the summation of the energy of the reactants, that is in this case going to be 436 plus 158. That will give me 194 that is kilojoule per mole. Then what about the total energy of the product? Well, the total energy of the product, as you can see, to be 2 multiplied by 568. So that will give me a 1136 kilojoules per mole. Now, how do we calculate the enthalpy change or the heat of reaction? Well, the heat of reaction or the enthalpy change, it is simply the summation of the energy of what we are calling as being, in this case, the reactant, if you want. Yeah, so the reactant minus the summation, in this case, of all the energy of the product. Let me just put up E there so that you don't get to confuse yourself. Allow me to just write it on top there so that we can actually conclude it. So in this case, when I look at this one, so what's the summation of the energy of the reactant? It is simply 594 minus that of the product, it is 1136. Now, of course, if you were to subtract 594 minus 1136, this is going to give you a negative 542. And remember, this is kilojoule per mole. That's what we mean. So now, is this an exothermic or an endothermic reaction? If you look at what you have there, is this an exothermic or endothermic reaction? Of course, we can actually conclude that this is an exothermic. This is an exothermic reaction. So this is an exothermic reaction. And why are we saying that it is an exothermic reaction? Remember, the energy of the reactant is actually less than the energy of the product. And you can able to see that negative is simply telling you that energy is actually, being given out. So that's the way you can actually determine that. Please watch out for more of my videos on this. I'll show you some examples, some practical examples, so that you can actually become familiar with how to go about this. Thank you so much, for watching.